Yes. Welcome to the seminar by Alexandros, who is visiting until tomorrow, I guess. And
Here, yes. Yeah.
and we'll talk about future markets.
Yeah. Many thanks to Kilian and Susanna for inviting me to visit, and for Jakob for organizing everything with the talk and finding a good time and everything. So this talk is going to be about problem that is in the area of economics and computation, or these so-called Fisher markets. But I promise you that there's going to be some, I think, nice complexity stuff in there. So even if you don't care about the economic stuff at all, there's still going to be something interesting for you to go. So this is joint work with my co-authors, Archie from Holloway, John from Liverpool, and Series from Essex. So it's full UK team. Right, so I'll start with motivation first of all. So what are these Fisher markets? So in a Fisher market, there is a set of divisible goods, M divisible goods. And what is a divisible good? A divisible good is a good that can be divided arbitrarily into smaller parts. So for example, water or sand, oil, flour. Probably rice, you can also think of it as a divisible good. But a car, not really a divisible good. You cut it into parts that kind of lose its value. Okay. So here we're talking about divisible goods. So think of water, oil, and these kinds of things. So there's M divisible goods, and there is, we're going to normalize to say that there's one unit of each good, meaning there's 100 liters of water or 200 liters, doesn't matter. We're going to call that one unit. So there is one unit of each good available in the market, and then we have N buyers who come to the market. And the idea is that these buyers are going to buy stuff. They're going to buy goods. Okay. So these buyers, they come with two things. First of all, each of them has a budget. So this is just an amount of money that they have. And the second thing that they have is they have a utility function over these divisible goods, telling us how much they like each of the goods. And the way this utility function works in general is that for any allocation or for any bundle of goods, for example, 0.3 units of water, 0.5 units of flour, and 0.7 units of rice, if the buyer gets that allocation, the utility function maps this allocation to a real value and tells us how much value the buyer has for this bundle. Okay? We're actually going to focus on a special case where the utility function have a nice structure. So then this is the mathematical definition, but it's much easier to explain just with a picture. So the idea is that for every buyer I, and for every good, so this is good one, the buyer is going to have a piecewise linear utility function that is concave. So the more the buyer buys of it, the amount of utility that the buyer gets can go down. So this is so-called increasing marginals. And the buyer has a separate such piecewise linear function for each of the goods. And the total utility that the buyer gets from a bundle of goods is just the sum of the utility that the buyer gets from each individual good. Okay, so this is what the separable part means. Additively separable, you just add the utility you get from each good, and then for each good, it's piecewise linear concave, like this. Okay, so these are going to be the simple utility functions that we'll consider. And a particularly nice special case is when these functions are not piecewise linear, but just actually linear. Okay, so they have a single linear piece. All right, so we said the buyers have a budget that they're going to spend to buy stuff. That means that the goods have to have prices. And so if we assume that we're given a price vector, so a price for each of the M goods, what the buyers are going to do is that they're going to try to buy an optimal bundle given these constraints. So one of the constraints, okay, they have to buy some non-negative amount of each good. And well, they have a limited amount of money. So this constraint here encodes the budget constraint. So what is it saying? It's just saying that the amount of money that they spend, so buyer I spends PJ, the price of PJ, times how much PJ the buyer is buying, and you sum that over all goods, and this is how much money the buyer is spending to buy this allocation xi. And this has to be at most the budget of the buyer. So these constraints, the feasible set of this optimization problem is just all the allocations that the buyer can afford to buy, okay, given its budget. And then you want an allocation that among these is optimal to buy. Okay, so this is what the buyers do. They come with a budget, they see some prices, and they buy an optimal bundle. So we can denote the optimal set of optimal bundles like this. And in general, note that there might be more than one optimal bundle. So this is really the set. Okay, so now we can finally get to the solution concept. So the solution concept is the so-called competitive equilibrium or market equilibrium. And it's a particular price vector together with an allocation saying what each buyer buys that satisfies two equilibrium constraints. The first one is that every buyer buys an optimal bundle. In other words, the allocation of buyer I has to be optimal at those prices. Okay? And the second constraint is that the market clears. So what does that mean? It means that if we take these allocations, one for each of the buyers, and we look at how much of good J is bought overall by summing what each of the buyer is buying, that total amount should be 1. Or recall that 1 is, we said it was 1 unit of the good. We normalize to say it's 1 unit of the good available overall in the market. So what these two equilibrium conditions are saying is every buyer is behaving optimally given the prices that the buyer sees when it arrives at the market, and everything is perfectly adjusted so that the amount that is bought of each good is exactly the amount that is available in the market. So in that sense, it's an equilibrium. So one way to think of this, why this is an equilibrium, is imagine that the amount that was bought was more than 1. What would happen then? But presumably, the price of that good would increase because you could make more money since people want it. And you can imagine the kind of local changes in the prices that maybe lead to an equilibrium. Any questions so far about the markets and the equilibrium condition? Yeah.
So in this setup, also all the buyers spend all the money, right?
Yes. Well, actually, if you assume that every buyer has some good where the slope is always positive, then that would be the case. It will always be reason to spend money because you get some positive utility out of it. There is an annoying special case where after some point the utilities could be flat, but actually we're going to exclude that case anyway because it's not so interesting. So yes, particular, it will be in an optimal bundle, this constraint will be tight. Okay, so why are they called Fisher markets? Because so far it has nothing to do with fish, right? Indeed, it has nothing to do with fish. But it's this guy, Irving Fisher, who came up with introduced these markets, and he is a major American economist. Although I was looking at his Wikipedia page yesterday, and he's famous for stating a few days before the Wall Street crash of 1929 that the prices will remain high and they accurately reflect the value of the underlying stock market assets. But his economics work, theoretical work is great. Okay, so this is a nice, pretty natural notion of an equilibrium, and the natural question is it always guaranteed to exist? Okay, is there always such a nice, stable state for the market? And the answer is yes. So if you assume this sufficient condition, which is what I mentioned about your question, essentially that for every buyer I, there exists some good, such that the utility function remains strictly increasing. In other words, in economics, they say the buyer is not satiated. If the buyer gets more money, the buyer will buy more stuff, get more utility. Then there is, under this nice condition, can show that every Fisher market always admits at least one market equilibrium. And I guess this result was proved earlier, but for this particular condition, it's Maxwell who stated that. So this is nice. It tells us that this nice solution concept is always guaranteed to exist. But the natural question is, can we actually find it? So the existence proof that shows that it exists, it doesn't give us a constructive polynomial time algorithm to find them. Okay.
Can
So
you
it's,
say something about how sensitive you are to what the utilities look like? Because I mean, you made them super nice, right? Piecewise
Yes.
linear.
So
Is
mainly
concavity is like important?
exactly. So concavity is the main thing, and the non-saturation.
Yeah.
No, the two main things. So yes, I'm focusing on these nice utilities because we'll mostly be talking about hardness. But it's nicer to show it for more restricted models. But the existence result, yeah, for in general, you need concavity essentially is the main thing you need. So you can have much more complicated utility functions that are not separable, that have complementarities. You need to have both of these items to get value out of them. Or if you have this one, then this one doesn't give you any value anymore. You have all these complicated behaviors as long as you are complete. So the proof of existence uses topological fixed point theorems. You use Bauer's fixed point theorem or Kapitani's fixed point theorem. And the important thing is that there's no general algorithm that finds these fixed points. Okay. So it's not clear how to find it, even though we know it exists. So what do we know? For some special cases, actually, it can be found. In particular, this particularly nice case where the utilities are actually linear, not piecewise linear. Turns out that there is a polynomial time algorithm for that setting, and it's not that complicated. It's you can express the problem as a convex problem. Turns out, and that program gives you the optimal allocations, and its dual gives you the optimal functions. So this is not too hard. There's some people who also come up with combinatorial algorithms that don't use optimization to find the solution. Another case that is easy is if you have a constant number of buyers for goods. That's also can also be done in polynomial time for those piecewise linear utilities. So what about if we don't have these two constraints? What if we have these piecewise linear utilities and we have any number of buyers and goods? There's no polynomial time algorithm known for this case. So the natural thing to try to do is to try to provide some evidence for why this is the case. Try to show a hardness result. So can we show a hardness result for this? The answer is no. And the reason is that the problem is a TFNP problem. And because it's a TFNP problem, we can't really hope to prove NP hardness because that would imply that NP equals quantity. So what is a TFNP problem? A TFNP problem is a problem that always has a solution. And given any candidate solution, I can efficiently check if it is a solution. So I can check the polynomial time. And our problem here has both these properties. I already told you that there's always a solution. And it's not too hard to see that if I give you prices and an allocation, you can efficiently check that the two conditions of equilibrium are satisfied. Okay. So what do we do when we are presented with a TFNP problem? We want to provide some evidence that it's unlikely to have a polynomial time algorithm. Well, so people have defined these subclasses of TFNP. And it turns out that you can actually show completeness results for these subclasses. For example, the problem of computing a Nash equilibrium in a game has been proved to be PPAD complete. The problem of computing a locally maximal cut is known to be PLS complete. The problem of computing a solution, a fixed point of gradient descent, is known to be CLS complete. So what do these results mean? If you prove completeness for one of these classes, that provides evidence that there is no polynomial algorithm. And why is that? Well, the first reason is that by now there's quite a few problems that are bundled in those classes that we know are complete for those classes. And so if you came up with a polynomial time algorithm for any one of them, that would make the whole class collapse. You could solve a bunch of problems at the same time. And so this gives some evidence that at least simple ideas are not going to be enough to come up with a polynomial time algorithm. We need to come up with some revolutionary new idea. And the second reason why we believe these problems are hard is, in particular, these classes are known to be hard under some cryptographic assumptions. So that means that if you come up with an algorithm that solves Nash equilibrium efficiently, then you kind of disprove some cryptographic hardness assumption that people in cryptography kind of believe, mostly believe. So these results have been improving over the past few years to more and more believable cryptographic assumptions. So takeaway from this slide is if you show completeness for one of these classes, it seems unlikely that we'll be able to find a polynomial type algorithm. It would take some revolutionary new ideas. So what is known for these piecewise linear utilities? The problem is actually known to be PPAD-hard. Okay. So if you don't have those two restrictions, then we don't expect that there will be a polynomial time algorithm that finds such a marked equilibrium. And what do we do in computer science when the problem is hard? We try to relax it, we add some approximation to see if that helps us solve the problem. So the way this marked equilibrium problem is usually relaxed is that the second condition, the clearing condition, is relaxed in the following way. Instead of asking that the market clears perfectly, we ask that it clears up to epsilon units. So instead of the amount of good J that is bought being exactly 1, we say we're okay with if it's between 1 plus epsilon and 1 minus epsilon. Okay? So this is a relaxation of the problem. Does it make the problem tractable? If epsilon is inverse polynomial, the problem remains hard. And the question was, what happens if epsilon is constant? Is there some sufficiently small constant such that computing this kind of epsilon approximate equilibrium becomes tractable? In particular, is there some sufficiently nice small constant for which you could solve this problem efficiently? So in our work with the same set of authors, I guess year ago, we proved that this remains hard. So it remains hard to show find an epsilon approximate market equilibrium even for a constant epsilon. And in fact, the constant that we show it for is, we're not ashamed to write it down explicitly. Yes.
Can you say something about why this is a natural relaxation?
What is natural?
Yeah, or like the right thing to, yeah.
Yeah. I mean, I have some disagreements with why it is natural. Right? This is the one that is usually considered. I suspect that it just happens to be that some algorithms, not efficient, some kind of pivoting algorithms that are exponential in general, but that are maybe nice to run in practice, that they actually come up with solutions where the approximation occurs there and not in the optimal bundles. So you can imagine that every step you change the prices a little bit, you update the bundles to be optimal, and then you try to make this closer to 1. And then this would be the natural. But yeah, the second half of the talk will be about considering a different type of approximation.
Fair enough.
Might be viewed as more natural. So we show that with this type of approximation, the problem remains hard, even if you have constant approximation. So the way we prove this is that we reduce from a problem called the pure circuit problem, which is known to be PPAD complete, and as a result, it establishes that this is PPAD-hard. And so now I'm going to tell you what this pure circuit problem is. And this is the more complexity part of the talk. And if you only remember one thing from this talk, I'd be happy if it's this pure circuit problem. So what is this pure circuit problem? So the input to the problem is a Boolean circuit, but there's a twist or a few twists. The first twist is that the circuit is allowed to have cycles, so directed cycles. So that means that you might have a value that appears in the circuit. There are gates that use the value, and then cycles back. Okay. The second twist is that instead of just allowing the Boolean value 0, 1, we allow a third value, which is this, use the spot symbol, but I'm going to call this value garbage. And hopefully the reason why will become apparent in a bit. And the third twist is that in addition to the standard logical gates, the circuit also has an additional new type of gate that we call the purified gate. And this is where the problem takes its name from. So let's define the problem. The input is going to be this weird Boolean circuit that can have cycles and these weird gates. And the goal is to assign a value to each node of the circuit, a value that can be 0, 1, or garbage. so that all the gates are satisfied. And let me explain what I mean by a gate is satisfied. So let's start with the simplest type of gate, the NOT gate. So NOT gate has one input node, one output node, and what it's supposed to do is to compute the NOT. So what does that mean? If you assign value 0 to the input node, in order for the gate to be satisfied, you have to assign value 1 to the output node. Similarly, if you assign 1 to the input node, you have to assign 0. So you're just computing a NOT. What happens if you assign garbage to the input? In that case, the gate will be satisfied no matter what value you assign to the output node. Okay, so you can give value 0, 1, or garbage. Doesn't matter, the gate will be happy, it will be satisfied. Let's move on to a slightly more involved gate, the AND gate. The AND gate works in a similar way. If the inputs are normal Boolean bits, 0, 1, it just computes the AND. Okay, so the gate, in order to be satisfied, has to output the AND of its inputs. What happens if one of the inputs is garbage? Well, if it's garbage and 1, then again, you're allowed to output whatever you want. But if it's garbage and 0, then I want you to output 0, okay? So this is a bit more special, but kind of makes sense. You know, the AND of 0 and no matter what will be 0. So the gate has to do this, has to output 0 in that case to be satisfied. Okay, so far we've seen these standard logical gates. They do what you expect of them when the inputs are normal pure bits. And when there's garbage, the gate has more freedom in terms of what it can do in most cases. What is this new purify gate? So it's kind of a weird gate. It has one input and two outputs. And what does it do? If you give it input 0, then the gate spits out 0 and 0, just copies the input. Similarly, if you give it input 1, it outputs 2 1s. And what does it do if you input garbage? This is where it gets interesting. If you input garbage, then the gate can output whatever it wants, except for this. This is forbidden. It's not allowed to output garbage and garbage. In other words, it has to output something where at least one of the outputs is a pure bit. And that's why it's called a purify gate, because it takes something that's garbage and somehow it manages to output at least one pure bit. There's no guarantee about what the bit is going to be, 0 or 1. There's no guarantee about whether it's going to be here or here. The only thing that's forbidden is it's not allowed to output garbage. It can do whatever else it wants. Okay. So these are the gates. This is what it means to satisfy a gate. And so let's now take a look at why we introduce these various twists. So I said that I want to allow the circuit to have cycles. Why do I want to allow the circuit to have cycles? Well, if the circuit doesn't have any cycles, then it's easy to find an assignment that satisfies all the gates. I can just, for example, start by assigning 0 to the sources, and then just compute through like I would with a circuit. And I found an assignment that satisfies all the gates. But we want this problem to be hard, we want it to be PPAD complete. That's why we introduce the cycles.
You don't care about the output gate at all.
Sorry?
You don't care about the output gate.
There's no output gate. Just a circuit that involves gates that can have cycles, and there's no particular node that's designed or designated as being the output node or input node. There's nothing like this. So we want the circuit to have cycles in order to make it interesting and not trigger every point all the time. Why did we allow this additional garbage value? Well, the second thing we want this problem to be PPAD complete. And in particular, that means it's in TF&P. In particular, that means it has to always have a solution. And if you don't have this additional garbage value, then already for a very simple circuit, this triangle of 3 NOT gates, if you don't have this garbage value, then there's no way to assign values to the nodes such that all the gates are satisfied. Okay, no matter what I set this to, I have to set this to 1, this to 0, and then this gate is not satisfied. There's no way to satisfy all 3 gates at the same time. Allowing this garbage value gives, for example, this trivial solution. But more generally, it ensures, this is not trivial, it ensures that for every instance, there is always an assignment that satisfies all the gates. So this is why we need this garbage value. And the third thing I mentioned is we introduced this additional purify gate. Why did we need to do this? What happens if I have a circuit that only has the standard logical gates and not this purify gate? Again, it's very easy to solve. I can just assign a garbage value to every node. And if you remember how these gates work, if the inputs are all garbage, the output can be garbage. It's an acceptable output and the gate is satisfied. So I need all of those twists that I mentioned in order to make this problem both always have a solution and at the same time not be trivial equal in number. Okay, so it's kind of hitting the sweet spot. Okay, so this is what an instance of pure circuit looks like. I give you this kind of Boolean circuit with a special type of gates, and you can have cycles. And I ask you assign a value to every node such that all the gates are happy. Okay, and if you start trying to solve these things, you will see that it's not always very easy. So there's no clear polynomial time to do polynomial algorithm to do this. And indeed, we show in prior work, same set of authors, that this problem is PPAD. Okay, so we don't expect a polynomial time algorithm to solve this. And what this tool is made for, it's made for proving that other problems are PPAD-hard. And the reason is because it's kind of the easiest PPAD complete problem in the sense that the constraints that you have to satisfy are very, very simple, very, very weak. Are there any questions about this circuit problem? So the fact that no matter how I set up the circuit, it always has a solution is not trivial to show. There is one condition, which is that I have to make sure that every node is the output of at most one gate. If I don't have that, then it might not be a solution, but this is easy to enforce syntactically. That just in my circuit, every node is the most one incoming edge. To show that this thing always has a solution, you can use again a topological fixed point theorem to do that. But it's not immediate. I'm just looking at it. Okay, so this is the tool that we use to show this hardness result for Fisher markets for this constant approximation factor. I will give you a kind of a high level idea of how that reduction works, very, very high level. Yes.
Is there another of these also say like circuit?
Say it again, sorry.
Addition, multiplication gates.
Yes. So this is kind of the final stage of an evolution of problems that were introduced in prior work. The original versions of this problem had arithmetic gates and values that were not just 0, 1 or garbage, but values between real values, continuous values between 0 and 1. And you had to we had to satisfy, let's say, an addition gate up to some small error. That's how this is kind of the evolution.
Over a finite field.
Over a finite field, I don't see that, no. It would make sense, and in this setting, it would make sense as long as you can still guarantee the existence of a solution, which might be tricky or not obvious. But yeah, the origin story of this problem is that originally we had this type of problem, but the gates were kind of addition gate or multiplication by a constant, or even multiplication to inputs. And you had to satisfy all these arithmetic operations in a circuit like this that again had cycles. This encodes kind of a fixed point problem. This version of the problem is the weakest version that we know to be PPAD-hard because the constraints of every gate are extremely weak. Okay, so to show this harnessing of Fisher markets, we're going to take an instance of pure circuit, and we're going to construct an instance of the Fisher market problem, such that any market equilibrium of this Fisher market gives us a solution, an assignment to our original pure circuit instance. And the idea is that we're going to create one good for each variable, for each node of the pure circuit instance. And the price that it will have at equilibrium, we're going to interpret that as telling us what value we should assign to the corresponding node in the pure circuit instance. So if the good has a low price at equilibrium, then we're going to assign it value 0 in the pure circuit instance. There's a high price, we're going to give it value 1. There's a price between those two low and high prices, then we'll give it the value as garbage. So how do you implement gates in the market? How do you implement, for example, a NOT gate? So the high level idea is that, so this is the input good, this is the output good. What you want to do is you want to ensure that if this has a high price at equilibrium, then this has to have a low price. And if this has a low price, this has to have a high price. Okay? And so you introduce a buyer that we call the inverter that has the following utility function. For the input good, it goes up steeply and then is flat. And for the output good, it just remains linear with a moderate slope. And so the idea is that because this part is steep, the inverter is essentially, in order to buy an optimal bundle, the inverter is forced to buy this good first, up to this amount, and then spends the remaining budget that is available on the output good. So what will happen if the input good has a low price? In that case, the buyer is going to spend a small amount of money to buy this because the price of this good is low, and will have essentially most of its budget left to spend on the output good. Now, because the output good has to clear, meaning that at most, or exactly 1 unit must be bought, but in particular at most, if the inverter is spending that much money on the output good, it means that its price has to be pretty high. So that spending that much of money doesn't mean buying 2 or 3 units, more than 1. On the other hand, if the input price is high, because the inverter has to buy this first, because the slope is very steep here, it gives a lot of utility, the inverter will spend a lot of money to buy this amount of good, and then we'll have only a small amount of its budget left to spend on the output good. Now, because the output good has to clear, which means 1 unit must be bought, at least 1 unit must be bought, that means that the price has to be pretty low, so it clears with a small amount of money spent on it. Okay, that's the general idea. So we call this the inverter because it kind of turns a high price into a low price and a low price into a high price. To make this work nicely, you also have to add an additional good, kind of a reference good that has a more or less fixed price. And this will serve to kind of cap how high the price of this good will go. But this is a detail. I think I want to say more about this. So we use similar ideas to implement the other gates. So it turns out you can, by adding 2 input goods, you can implement a NAND gate. And by using a variant of the NOT gate, you can implement a purified gate. In the interest of time, I will not say more about this at this point. The general high-level idea is you can create goods that correspond to the nodes and buyers that implement the gates, and you can encode this pure circuit problem in this Fisher market problem. So the bottom line is that the problem remains hard, even if you relax this clearing condition and allow approximate clearing. So the natural question is, what happens if we relax the first condition of the equilibrium? So if you remember, equilibrium, we have these 2 conditions, optimal bundles and clearing. What happens if we relax this condition, that every buyer should buy an optimal bundle? So this is how optimal bundles are defined, right? We ask the buyer buy something that gives them optimal utility. So the natural way to define it is to ask for something that gives multiplicative approximation to the optimal utility. In other words, to buy a bundle that is at least 1 minus delta optimal, meaning it gives the buyer at least 1 minus delta of the maximum utility that the buyer could achieve at those prices. Okay, so it's a natural way to relax this condition. And so we can consider, both relaxations at the same time. That's what we call an epsilon delta approximate market equilibrium. You allow epsilon clearing and 1 minus delta optimal bundles. So the question now is, does this make the problem easier, relaxing that condition as well? So this is what we knew from before, right? If delta is 0, if we don't relax the optimal bundles condition, problem remains hard. It's not too hard to use these same reductions to show that if delta is sufficiently small, so 1 over polynomial, the hardness still goes through. And so the main question was, what happens if delta is a constant? Is the problem still hard then, or does it become easier? So what we show in this work is that the problem remains hard for a constant delta, but we have to assume a conjecture to prove this result. Okay, so we assume the so-called PCP-for-PPAD conjecture. If you assume that, then it is true that there exists some sufficiently small constant delta, such that computing an approximate equilibrium where you relax the approximate bundle constraint, the optimal bundle constraint remains hard, and the result holds even if you relax both market theory and delta. In fact, we prove the factor here a little bit. Okay, so what this is saying is relaxing this first condition doesn't give you an efficient algorithm if you believe this PCP for PPAD conjecture. So what makes the problem harder? What makes it harder to prove a hardness result when you have this constant delta? Why do we need this PCP for PPAD conjecture? So the high-level idea is that because you allow these approximate optimal bundles, what happens is that for every buyer, it can spend a constant fraction of its budget on arbitrary goods. Okay, let's say delta is 1%. That means that every buyer in the market can spend 1% of its budget on some good that they don't have any value for, some arbitrary good. So in particular, all of the buyers, they can go and spend their 1% of budget that they can spend on anything and go spend it on the same particular good. And what that means is that this road budget can go and break one of our gates that we implement when we reduce from pure circuit. And so what this means is that we cannot ensure that we reduce from pure circuit, all the gates are going to be satisfied, because for any particular gate, you can use this delta fraction from every buyer in the market to go and break that gate. And more generally, you can actually go and break a constant fraction of the gates. So this is where the PCP for PPAD conjecture comes in. So this was originally introduced by Yurchenko, Dimitriou, and Rubinstein. And it can be stated in terms of our pure circuit problem that we saw earlier as follows. The conjecture says there exists a constant delta such that if I relax the pure circuit problem, and instead of requiring that all the gates have to be satisfied by the assignment of the output, you only have to satisfy some constant fraction, let's say 99% of the gates, but the problem remains just as hard. It remains PPAD-hard even if I only have to satisfy at least 99% of the gates. So this conjecture is open. We don't know if this is true or not, but it turns out that this is exactly the tool that we need in order to prove hardness for our relaxation of the Fisher-Markov problem. This conjecture was originally introduced in that paper as a tool that it was hoped would help for proving a particular hardness result for two-player games. But then it turned out in later work that this conjecture was not needed. And so it wasn't actually needed to prove that result for two-player games. And since then, the conjecture has been used in a limited number of works to prove some PPAD hardness results. So our result as a third paper here that shows another PPAD hardness result, assuming this conjecture. So hardness result holds even if the market has a lot of structure, particularly if all the budgets of all the buyers are the same, they're one. If the market has constant degree, meaning that for every buyer, the number of goods that they have non-zero utility for is constant, and for every good, the number of buyers who have non-zero utility for it is also constant. And the piecewise linear utility functions are also very simple. But the important thing is, unlike these previous papers, we can show that this conjecture is actually necessary to prove this result, or at least partially necessary. So we prove a partial converse, which is the following. Assume that you can show hardness for approximate market equilibrium, where you relax this optimal bundles constraint. And your market has this nice structure of all the budget being one, constant degree, and simple utility functions. Then that implies that the PCP-for-PPAD conjecture is true. So in other words, the PCP-for-PPAD conjecture is true, it is equivalent to this market problem being hard. And in fact, we can relax some of these things, and this compass still holds. So what this is saying is that for the first time, this conjecture is equivalent to something, meaning that actually resolving the conjecture is necessary to understand the complexity of this market equilibrium problem. So there is no hope of proving PPAD-hardness for this market equilibrium problem without proving the conjecture. Okay? And so this motivates further the need to resolve this conjecture. Let's see. Okay, I have a bit more time, so I can tell you a little bit about how we prove this converge, unless there is a question before that.
Is there a particular, I mean, the name PCP for PPAD, would you expect there to be some PCP-like structures floating around, or it's more like it's that type of result? Or, I mean, the name?
I think it's that type of result, yes. We don't know how to prove it, so.
I mean, I'm going to ask, like, what would a PCP look like in this setting?
Yeah, so it's the PCP from the hardness of approximation. One of your PCPs. Okay, so what do we need to do to prove this partial converse? Well, we need to provide a reduction in the other direction. So we need to reduce from the markets to the pure circuit problem, to a pure circuit-like problem. And I'm going to give you a very, very, very high-level overview of how we do that. Okay, so you start from an instance of the market problem, and you want to show that you can find such a solution by reducing to the pure circuit problem. So this step one, the first step, turns out we can write the conditions of the market equilibrium with these pure circuit gates, constraints. You can encode it. And what that gives you is not what you want exactly, but it gives you a market solution where some of the goods can completely over or under clear, meaning some good might not be bought at all, some good, maybe 5 units of it are bought. And also some of the buyers do not buy approximately optimal bundles at all, so completely suboptimal bundles. And when I say some, I mean constant fraction. So constant fraction of the goods can be completely over clear or completely under clear, and a constant fraction of the buyers can buy arbitrary suboptimal bundles. This is what step one gives us. And then we kind of want to clean this up, because our goal is to get to a solution where all the goods approximately clear and all the buyers are buying approximately optimal bundles. So the first step towards that we can do is we can look at those buyers that are buying completely suboptimal bundles, and we can just change their allocation so that they are buying optimal bundles. And because the buyers that are completely bad like this, that we have to fix, just a constant fraction of the total number of buyers. What this does is that it adds some more over-under clearing potentially, or over clearing, but again, you still have most of the constant fraction of the goods that are over cleared. So now we have kind of fixed this issue, and we're left with this issue. We have a constant fraction of the goods that can over or under clear. The next step, which is the most involved one, is to remove the over clearing. So goods that are bought or more than one unit is bought. And we do this by using two procedures that we call the shift and burn procedure and the pump and shift procedure. And I'll say a little bit more about this on the next slide. Once the overclearing is fixed, the last step is just to fix the underclearing. And this part is quite easy, because if you remember, for every buyer, we can take a constant fraction of its budget and spending on whatever good we want. In particular, we can go and spend it on the goods that are not bought enough in order to make sure that they clear. So this part is easy. This is the most interesting part. The part where we remove the overclearing issue. So let's look at a very simple example just to give some intuition. So imagine that in my current state, this good is overclearing. What does that mean? More than 1 unit is bought. Let's say 2 units of this good are bought. What does that mean? It means too much money is spent on this good. Okay, I would like to halve the amount of money that's spent on that good. What can I try to do as a first step? I have this buyer here who likes both of these goods. So what I can try to do is to divert some money that the buyer spends on this good and instead make the buyer spend it on this good so that I lower the amount of money spent here. And at the same time, I can also, for this buyer, because the buyer, it's enough if the buyer buys an approximate optimal bundle, I can kind of burn some money, burn some small delta amount of money, meaning that the money just is not spent on either of these two edges. And I can keep kind of propagating that. And every time I encounter a buyer, I burn a little bit more money. So it turns out you can write a flow problem that does this maximally. And after you've done this maximally, this is the first phase, the shift and burn phase. You reach a point where you can no longer divert money or burn money to reduce the amount of money spent on this good. And in that case, what you do is you take the remaining component, connected component, and you increase the prices of all the goods by some constant small factor. What effect does that have? If you increase the price of the goods, that means that for a given amount of money spent on that good, the amount of good bought is lower, okay? Which is what we want. We want to buy less. So you increase the price of all these goods, and then you shift the money again, and then you just keep doing these steps, one after the other. And we can show that if you do this after a constant number of steps, you will have removed the overclearing completely from the instance. So this was this step here. And so at the end, what we obtain is a solution where there is no over or under clearing, and everyone is buying an approximately optimal bundle. So this is the idea of the reduction in the other direction. Okay, so I think it's time to end. Let me mention the open questions. The first one is, well, we now know that we kind of need to figure out what's going on with this PCP-for-PPAD conjecture. It's necessary to understand this problem. So the first open question is to prove this conjecture. And the second question is to disprove this conjecture. And in general, I would be interested to find other problems that occur kind of naturally and that turn out to be equivalent to this conjecture. So for now, this is the only example that we have. Thank you.
Is your main focus on the first or the second item on this list?
My guess is that the problem is hard. So that this is true or a weaker version of this. So there is an intermediate case where finding an assignment that satisfies a constant function of the gates is not in polynomial time, but it's also not PPAD-hard. It could be complete for an intermediate class like CLS or something. So the main question is this problem hard or not, rather than is it PPAD complete or not? My guess would be that it's hard, but who knows?
Are there also PCPs for other subclasses of PFN?
No, not yet. No, this is you can define a similar thing, I think, for some other classes, but they haven't been studied. So this is the first example we have so far. Yep.
So here you prove PPAD-hardness for those relaxations, but do you have any idea? So not completeness.
They are all in PPAD.
They're all in PPAD. Okay,
So
sorry.
it gives PPAD completeness. Yes.
Okay.
Mm-hmm. Yeah.
And also, how did you come up with that purified circuit problem? Is there any intuition behind that?
The pure circuit problem?
Yeah.
Yeah, I mean, the intuition is that because this PPAD class corresponds to fixed point problems,
Mhm.
in prior work to prove hardness results, there were problems defined where these gates, instead of being Boolean, but kind of arithmetic gates, as I mentioned briefly earlier. And so this is kind of taking these arithmetic versions and pushing the allowed error that you allow every gate to the maximum, meaning making the gates as big as possible, and you get something like this. So that's how you end up with this problem. Kind of it's a fixed point problem where the constraint for each gate is as weak as possible, which means it's as easy as possible to implement when you're reducing from this to another problem.
And do you have like, I don't know, maybe some derivative of this pure circuit problem that would be like complete for CLS or PPAD or related classes?
No, we don't have that. No. That would be interesting, especially for CLS.
In case of like linear utility function, then phi would just buy one good, right?
No, so what can happen is you can be different between multiple goods.
Yeah.
And then you might buy a bit of this, a bit of this, a bit of this. But these things are much easier in the case of linear goods, and that's why you cannot implement these more complicated constraints that we were hardness results. Thank you for the question.
Can you explain how do you move from the continuous fixed point theorem to like three options?
So you're talking about the partial converse of this part?
No, just what this is PPAD complete.
Okay, so you mean for the pure circuit problem?
Yeah.
Yes. So even though we think of PPAD and Bauer's fixed point theorem as a continuous thing, ultimately all these different B classes are discrete. And so even when you say finding a Bauer fixed point is PPAD complete, what you actually mean is finding an approximate Bauer fixed point. And so it's actually discrete, like a grid version of the problem.
So the size of this circuit will be somehow related to the bit complexity.
Yes, exactly. So in order to prove that the pure circuit problem is PPAD complete, you reduce from some version of Brouwer, and you're going to use some bit decoding, and you're going to rely on the fact that you're looking for a approximate solution to be able to represent everything with bits. Yes, so you're not doing exact computation.
So is it clear what the economists think? I mean, out there in the real world, do markets clear in general?
It's a good question.
Because either markets don't clear, right? An economy is broken, or somehow maybe the markets that are out there in the real world are so nice that, you're just studying the pathological examples, which raises the question of, is there some kind of, average case notion of hardness, which you'd say the typical market is PPAD-hard?
Yeah, so what is the structure of these natural markets that makes them easy, potentially? So people study dynamics of markets. So if they find some simple dynamics of these are the current prices, the market doesn't clear, the prices will move in a natural way to fix this. And then they ask the question, do these dynamics converge to an equilibrium or not? And then there's positive and negative results, depending on how complicated the market is. For linear utilities, I think there are some positive results, but for the cases where it's PPAD-hard, the dynamics do not converge efficiently they don't converge at all to a market equilibrium. So people study these dynamics. Now, for actual real-world markets, I don't know much about those.
Okay, yes, thank you.